Okay, good. All right. So good morning and good afternoon and good evening, I presume. And I really thank you for for organizing the workshop. To be honest, I've actually been a bit away from samarium hexaboride for the past year or so, but I'm happy to tell you about the status of our work on the magnetism in this material. And I'm looking forward to learning more about the recent developments. The picture is from our beloved Homewood campus that looked like this when I last saw it. But now it may look more like this, actually. I haven't been there for a while, so we're not quite sure, but we do have snow here today. I'm going to talk about, my talk will have two parts to it. I will talk about the intrinsic magnetism of samarium hexaboride and extrinsic magnetism of samarium hexaboride. I think both of them are interesting to understand the properties of the material. Though I have to say that I was very impressed by Suchicha's presentation, and I can see that many of the things that we have found in terms of extrinsic effects in the material, she's looked very carefully for those and been able to eliminate those as being related to the de Haas van Alphen effect that's being reported. But still, I think these properties and behaviors of the compound under various kinds of doping are quite interesting and important to understand as well. So the first part of the talk, I'm going to discuss the intrinsic magnetism. Let's see, these are the collaborators, and I wanted to mention in particular Wes Furman and John Liner, who respectively had this as their main topic for their graduate work and their postdoctoral work, and Predrag Nikolic, who did the theory that I'll briefly describe, but he's actually on the Zoom call, I believe, and so maybe he can answer any tougher questions in theory. And then Syed Copaye, Terrell McQueen, and Adam Fellon, who grew various compounds, mostly floating zone samarium hexaboride, but also actually flux-grown materials together with Wes Furman. Okay, so let's talk about the intrinsic magnetism of samarium hexaboride, and this will mostly be talking about our neutron scattering work and our studies of the spin resonance as a function of energy, temperature, and magnetic field. But first, let me say a few words about the mixed valent character. You're aware that this is a mixed valent compound, and this can actually be seen directly in total electron yield X-ray absorption spectroscopy, which is shown here as a function of energy. And there are features in the absorption spectrum that are known to be associated with samarium 2+ here and samarium 3+ here. And by fitting these kinds of spectra, one can actually directly extract the ratio of samarium 2+ and 3+, and this leads to an overall formal mixed valence of 2.6+ in this compound. Now, just to remind you, samarium 3+ is a spin orbital angular momentum 5½ Kramer's ion, and we expect some form of Kramer's doublet magnetism in this compound from that site, and from samarium 2+, that's an ion with total spin orbital angular momentum of 0, and we should expect some sort of singlet ground state magnetism with maybe a Van Vleck component to the magnetization. Okay, now using neutron scattering, we can look at the magnetism of each of those ions and each of those valences, and that was actually done by Pavel Alexeyev, who's our collaborator in all of this work, along with Jean-Michel Mignot. And they've actually worked on this compound for a very extended period of time and have multiple really wonderful papers on it. And what's shown here is their measurement of the sort of broad spectrum of magnetic excitations, from which they pull out a dominant component actually that's associated with the 4f6 ion, so the samarium 2+, and a transition from J = 0 to J = 1. But then they also see intermultiplet transitions from 5½ to 7½ associated with the 4f5 ion. Now, all of these features have the F electron form factor, which is shown in the inset associated with them. Okay, now what about the Q = 0 magnetism that we measure, for example, in a squid magnetometry? And shown here's some data from quite some time ago, 1971, by Nicholson et al. in Physra B. where they measured the susceptibility up to very high temperatures, and they compared it to the expected susceptibility associated with the Van Vleck contribution from the 4F6 samarium 2+ ion. And actually, most of the susceptibility that's in this temperature range can be associated with that intermultiplet transition. So when there is this shown here on the right, when I show the field-induced magnetic Bragg diffraction, actually, this is a spin-polarized experiment by Buchel et al. From 1995, where they apply a magnetic field and then measure the flipping ratio on Bragg peaks in the material, and from that they can extract the magnetic amplitude contribution to each of the Bragg peaks, and they actually are able to show that that induced magnetization does follow the F electron form factor. So I'm saying all this, and you might say, well, this is kind of strange that he's talking so much about the form factor. It's because later we will have the surprising result that the inelastic scattering actually carries a d electron form factor, which is quite a surprise to us, actually. Good. All right. So then I'm going to turn to the finite Q magnetism, and so inelastic magnetic scattering. And first, I'm going to show energy integrated scattering. Now, this is not like the full energy range, so it's a fairly concentrated range of energies between 5 millielectron volts and 20 millielectron volts that's being integrated over. And then we're showing the momentum dependence of the magnetic scattering. And we've indicated the high symmetry points in the brilliance zone, the X point, the R point, the M point of the cubic structure. And you see that intensity accumulates at these high symmetry points in the brilliance zone. We also notice that you actually see intensity again in the second brilliance zone. Also the X point but now removed at a finite wave vector, reciprocal lattice vector G, and you also see some intensity at that point. And this is important to us because it indicates that this inelastic magnetic scattering actually is associated with the simple cubic lattice, and it does repeat in reciprocal space as we expect from Bloch's theorem. Okay, so this also allows us to then look at the relative intensity, let's say between this X point and the X plus G point. And if we were dealing with simply magnetic scattering from the F electron, then the ratio of intensity between those 2 points, so from X to G, should simply be given by the magnetic form factor for the F electron, which has been measured, as I indicated previously, for the induced moment form factor. And so this is what I've written up here. The ratio intensity at those points should be given by the ratio modulus squared of the form factors at those particular wave vectors. And so shown here is the squared, it's the intensity as a function of wave vector transfer. And there are kind of precious few points on this curve, but we think they're important. We have the X point where we had the most intensity, and then the X plus G point where there was considerably less intensity. And then another point, which I didn't point out in the previous graph, where there's even less intensity. So, so this is the decrease in intensity obtained from those data as you move through different brilliance zones. And it's then compared to the solid black line, which shows the form factor for the F electron, for the 4F electron of samarium. And you see that actually the data is very much is very different from that. In fact, this is really quite a, to me, it was a very surprising result because we've been, studying heavy fermion systems as an example, and there was always an attempt to understand, to look for the impact on the form factor from the formation of F electron bands. But this, I think, was never really successful. The form factor kind of looks like the F electron all the time, but here you really have a sharp, deviation from the F form factor to something that looks more, in fact, like the 5d electron form factor that you would associate with samarium 3+ ion. So that's the dashed line shown here. Okay, good. So that's an important result to bear in mind. So how should we then be thinking about this magnetic scattering? And I want to bring to mind the way that we tend to think about magnetic scattering from a itinerant magnetic system such as chromium. So chromium is the sort of typical spin density wave system formed due to the Fermi surface nesting. And when you look at the magnetic scattering from this kind of compound, you basically see inelastic scattering at very selected points in reciprocal space that can be linked actually to these nesting conditions that translate empty to occupied states on Fermi surfaces. And so here you see the Q minus and the Q plus vector that have to do with these translations where big kind of areas of the Fermi surface kind of match onto each other. That's where you see a lot of intensity. As you come up in energy, then because of the dispersion of these quasi-particles, then actually there's more momentum space accessible, and you get broader and broader features as you come to higher energy transfer. And conversely, as you go to low energy transfer, eventually all of this collapses to the Bragg peak associated with the spin density wave. So it's there is kind of a well-known kind of connection between the momentum dependence of magnetic neutron scattering and the band structure of correlated electron systems. Okay, so here we are then dealing with a hybridized insulating conduit, it's a hybridized conduit insulating system. And here's a sketch of the 5d electron band with the much more weakly dispersive 4f electron band passing through, and then having the hybridization gap open up. And we can then consider excitations which connect points with high density of states to each other, and they would then be expected to produce high intensity. And actually, the way that we tried to analyze the data was to develop a phenomenological band structure which is based only on this diagonal hopping term. So from that we can form bands associated with the d electrons and the f electrons. We can then calculate the hybridized band structure, and then we can from that calculate the Linhart stability and compare that to the measured neutron scattering. So in that way we can, in a sense, infer by by looking at the neutron scattering data what the band structure might actually look like. And so this is what we've then done here. This was actually, I should say, the work of Wes Furman together with Predrag Nikolic. The comparison here of the experimental data that I showed initially, just the energy integrated data, to the Linhart stability calculated for this band structure that only has the diagonal hopping term. And you're actually able to reproduce these features in the scattering pattern. And I should say that the form factor that has been applied here has been the d electron form factor, even though there's not a theoretical justification for that in this phenomenological approach. So then one can then look at the inferred band structure, and that's what I've done here. So it's shown the band structure that provides that calculated momentum-dependent neutron scattering. And one finds that, in fact, this is a topological, a strong topological insulator, in the sense that the topological index is non-trivial as a result of a different parity at the x point and the m point, because at the x point you have the f band lying lowest and being occupied, whereas at the m point we have the f band lowest, and at the x point we have the d band lowest. So we have different parity at those points, and so the product of the parities becomes negative, and so the inference is that it is topological phenomenological band structure that we infer, and so actually it's interesting, it's kind of in hindsight looking at that, that the inelastic scattering pattern actually itself tells the story of whether it's a topological state or not, in that the presence of scattering at the x point and the absence of it at the m point indicates the opposite parities at these locations, and that then can can support the inference of a topological band structure. But I should say that really one needs to go through the process of developing a phenomenological band structure, comparing to the experiment to, in general, be able to do that. But I'm highlighting the capacity of inelastic neutron scattering to actually access these kinds of features of the relevant band structure in the correlated electron systems. Let's look now a little bit more at the energy and momentum dependence of scattering in samarium hexaboride. So this is momentum dependence going through high symmetry reciprocal lattice points, and then energy transfer in the vertical direction. And you can see, again, that at the X point we have intensity, again at the R point we have intensity, but also that there is some degree of dispersion associated with that scattering. And actually it's a little easier to see if I make cuts through the intensity distributions at selected point in reciprocal space. And here we can see actually the X point, so that's a spectrum at the X point, and down here is a spectrum at the R point. And then in between we have cuts conducted at different wave vector transfers along this direction. And you can see that there is in fact dispersion. It's interesting that the R point is where we see the lowest energy excitation. It's slightly high energy at the X point, and then there's some dispersion in between those points. So this is a relatively sharp dispersive mode that kind of acquires high intensity at the high symmetry points in the reciprocal lattice zone. Now we can analyze these data by fitting these kinds of cuts, and from that we can obtain, and what is shown down here is the dispersion relation for this mode of excitation. We also show the width of the excitation with this resolution. It's actually essentially resolution limited with this in this particular experiment. Another point, which is maybe a somewhat finer point, but it's actually quite unusual in a sense to have a single mode of excitation that is able to turn on and off at different points in reciprocal space. This would not be, I don't think this would be possible to have, let's say, from simply a crystal field excitation, which had dispersion due to interactions. Then the oscillator strength tends to be constant in momentum space. But here you really have intensity that accumulates at certain points in reciprocal space. And I think that really only finds a good explanation in this by thinking in terms of the Linhart susceptibility. At least that's how I can see it being accounted for in a theoretical sense. Okay, the total moment sum rule allows us to say that the total strength of scattering related to the total strength of scattering expected for the 4F for the samarium site, and it turns out that the total scattering accumulated in this spectrum actually is fairly close to what you would expect for the 40% samarium 3+, I believe it is. Okay, so this Exciton has been, the sort of more comprehensive theoretical description actually of this excitonic mode has been looked at by Predrag Nikolic together with Wes Furman, and they use a slave boson mean field theory along with the RPA description of the fluctuations to obtain the renormalized hybridization gap. Show the formation of the exciton as a result of the fluctuations, and then actually infer the exciton dispersion using the RPA method. And all of this is actually based on the band structure that accounts for the momentum dependence of the scattering. And then on top of that, using these methods, it's possible to obtain this dispersion relation for the bound state that we've been looking at. And actually, there's a fairly good sort of agreement that can be attained between the theoretical description and the experimental data. Now, this motivated us to go back and look a bit more in detail at the nature of this excitation. And one of the questions that we had was, is this actually really a long-lived excitation, or is there some damping associated with that excitation? And so we used a TRISP instrument at the Munich facility to measure the line width of the excitation. And we find actually that it's a very, very sharp excitation with a half-width half maximum of 0.1 milli-electron volt. That means 1 Kelvin. We infer from that, considering the resolution, a finite realization rate of 38 picosecond. So there is some degree of damping that's visible, but really it's a very sharp mode of excitation that's seen there. The reason that it looked a bit broad in the previous data that I shown was that was a much coarser resolution experiment. The other question one could have is there some form of a spin fine structure or in this excitation? What is the spin nature of it? And for that we conducted experiments at high magnetic fields to see whether this mode would actually split apart upon application of a field. And that's actually a fairly challenging experiment. We did experiments at NIST using a 14 Tesla magnet and could see some kind of broadening of the peak. The gray data from 0 field and the brown data or the blue data from 14 Tesla. But then using the Helmholtz Center Berlin high field magnet at 24 Tesla, one can actually see the peak splitting apart into two structures or two maxima, both resolution limited. And from that, we can infer an effective G factor of 1.1, all of which is quite surprising, actually. And we don't have a proper understanding for this spin structure, and very interested in ideas for how that could actually take place. Okay, so that completes what I have to say about the what we'd call intrinsic magnetism that I expect to see in all fairly clean samples of samarium hexaboride. And I'm going to talk about the extrinsic magnetism that's associated really with impurity effects, but I still think that they're very interesting. And so here's shown the specific heat as a C over T plot versus T. And you can see in these particular samples, which are floating zone grown samples, a really high actually Sommerfeld constant that can get all the way up to around 50 millijoule per mole Kelvin squared. And as Suchicha showed in the samples that she's been looking at, they actually have 10 times less linear term in the specific heat. And so it's actually possible to modulate quite dramatically this the Sommerfeld constant in the compound by different preparations of the materials. And so in these flowing zone crystals, we've then looked at the low energy excitations that must be present to account for this linear term of the specific heat at low energies. And actually, these are measurements by Larita et al. From Peter Armitage lab. And these are measurements on optical floating zone grown crystals. And they do see actually, even at low temperatures, which is the blue trace here, a significant optical conductivity in the low frequency range. And that is, in a sense, consistent with there being charge excitations in that low energy sector in these kinds of crystals. Now, we also looked with neutron scattering for low energy magnetic excitations. And this was kind of a little bit of a dull experiment, but I think important experiment, because we didn't actually see any magnetic scattering in this particular energy window. So it was natural to look there because there is this Sommerfeld constant. And so we brought it to a high sensitivity machine, which is the MAX instrument at NIST. And I want to focus on this chart here. I agree it's kind of dull, but it's the difference in intensity between 9 Tesla and 0 Tesla. And that kind of measurements allows for a very clean subtraction of all kind of background components which are present in that particular energy range. And so this is really the high sensitivity that we can have towards magnetic excitations that we would expect to be field dependent. And so here's shown actually in normalized units. And this shows that we can put a limit down to about 2 millibarn per steradian per milli-electron volt. And you might ask, well, how should I get, what's the scale that how do I know the scale here? And I can show you here oh, sorry, I think here you can see actually this is the exciton itself. And so this mode, which is kind of the main strength of magnetic scattering in the compound, and you see that it reaches a strength of around 15 millibarn per millielectron volt per steradian. And so if I come back to this picture here, 15 is what is the scale that we saw for the exciton, and here we're seeing, you can think about what the limits are on it, but it's something in the range of at least 10 times less scattering in that range, maybe I would say 10 times less scattering than at the exciton in this particular energy range. So I think that's an important kind of piece of information as we think about how to describe the low energy states that exist in this compound. The other thing that we did was we looked at the magnetization of various samples, and we ended up focusing on for reasons that I'll try to explain, on the gadolinium dependence of the magnetization in these materials. And it's kind of a curious reason for that, which is because when we do neutron scattering, we need to use SmBg isotope, and it turns out that there's only one other rare earth atom which occurs as 154. I'll show you the chart in a little bit. And so we're able, particularly for gadolinium, to very carefully control the gadolinium content from very low content to as high content, obviously, as we'd like to put in. And so here is shown a plot of the magnetization for 1.85 concentration of gadolinium. This is simply per formula unit SmB₆ with 1.85% gadolinium. And then we go to our isotopic on, actually it's a Pavel's sample, Pavel Alexeyev's sample, which is the double isotope sample, a very clean floating zone grown sample with only SmBg in it. And this is what the magnetization looks like in that case. But if you subtract a linear term, you actually do see a little component that one would associate with a kind of a localized spin degree of freedom that's becoming magnetized. And then of course we're going to be looking at different concentrations as well. Now,
Collin, would you mind wrapping up in the next few minutes?
Okay, I will.
Thank you.
Up. And so let me just go to this point where I'm going to show you samples with different content of gadolinium, so from 0.04% all the way to 5%, and this is now in units of magnetization per gadolinium. And you see that as you go to high and high gadolinium content, there's actually suppression of the saturation magnetization per gadolinium ion. So it's as if the gadolinium ion itself is not able to express the full moment that you'd otherwise expect from it as we go to higher concentrations. And here is shown as a function of concentration that amount of suppression that is occurring in the magnetization per gadolinium ion. And on the next chart, I show the specific heat over temperature for various gadolinium doped samples, so from very pure to quite impure. And all of these data can actually be scaled on top of each other by dividing by this amount of suppression of the magnetization per gadolinium ion. And this indicates basically a link between the moment screening effect and the low energy density of states that reminds in the sense of what you expect in a Kondo screened system. And so it appears that there's a kind of screening that's occurring as you go to higher and higher gadolinium content in these crystals. And then separately from that, and now on samples which are not gadolinium doped, I'm going to show you X-ray circular magnetic dichroism measurements. Actually, let me, since I'm a little short on time, I will go to this chart. And it shows with X-ray circular magnetic dichroism, it's possible with valence specificity to measure the orbital and spin magnetization in the presence of a magnetic field for the SmBg2+ and the SmBg3+ sites within the material. And I should emphasize again that this compound is actually a floating zone. This is a floating zone grown high quality crystal that we're looking at here. And so we can separately look at the magnetization on these two sites. And it turns out actually, I think quite interestingly, that the magnetization of the SmBg is in opposition to the net magnetization of the sample. So SmBg actually, it becomes you could say diamagnetically oriented with respect to the main magnetization. And so it actually detracts a little bit from the overall magnetization in the material. And this reminds towards this screening effect and indicates that perhaps SmBg plays a role in this screening setup as one dopes the material with more gadolinium. Then I'd like to conclude and to say separately about the intrinsic and extrinsic magnetism is that in terms of the intrinsic magnetism, we've been able to measure the wave vector-dependent susceptibility and associated with Lindhaus susceptibility of a renormalized band structure, which is associated with topological band structure, topologically non-trivial band structure. There is an exciton which lies at 14 millielectron volts, which can be accounted for. Its dispersion can be accounted for using Slade boson mean field theory and fluctuations. We have shown that this mode has a long lifetime and that it splits in two components as a function of applied magnetic field. And then I discussed a kind of a Kondo screening type of effect that we think occurs as you put increasing contents of gadolinium into the material. And with that, I'd like to take any questions. Thank you for your attention.
Okay, thank you very much, Collin. Okay, we've got an immediate question from Chandra. Piers, I know that you also had a question that you put in the chat. If you wanted to ask that one now, then I'll let you go first. Otherwise, I'll turn it over to Chandra.
Okay. Thank you. Can you hear me?
Yes.
Yes, go ahead.
Okay, good. Well, I had the one in the chat was a very simple one. It was really questioning how you can see a low energy desert in your inelastic scattering, and yet the NMR purportedly has a Kringer response at low temperatures. Would those two results be consistent?
I don't think they're in hard experimental conflict with each other, because the NMR is really probing an even lower energy range than what we can access.
Okay.
So you have to think about that as that would be the limit. Frequency goes to probably much, into the megahertz range of chi double prime over omega.
Right. So
we cannot get to that range.
So maybe you're just missing that because of the ranges. Okay. And how do you know your exciton is a surface excitation rather than a bulk excitation? You mentioned that in your conclusions.
No, that was that I can't say. So I might have said something.
Would the cross section be big enough if it were on the surface?
Yeah, no, I don't think it would be big enough. No, this
has to be a bulk.
Oh no, sorry. Yeah, that's this point here. Yeah. No, what we're seeing in terms of the exciton, that's really is a bulk effect, and because it carries most of the spectral weight that you expect from that samarium ion. But what I was trying to say here is that this is sort of a hypothesis we could say is that we know that under high pressure, as was mentioned previously, there's a transition into a metallic state that may alter magnetic order, and we're considering, we have done some experiments as well, the possibility that this would then push this exciton mode to zero energy, and then that would be the wave vector where we would have the magnetic ordering. But we're looking at a bulk exciton.
Thank you very much.
Okay, I think Chandra was next. Chandra, go ahead.
I'm very intrigued by this twofold splitting. This is seen, the exciton is seen by neutrons. Is this in a neutron inelastic experiment?
Yes.
Or an optical experiment?
This is a neutron inelastic experiment.
So neutrons are only supposed to see spin 1 excitation, and spin 1 excitation usually split in magnetic field into 3 parts. Only spin half excitation split into 2 parts, and neutrons are not supposed to couple to spin half excitations. Do you have? This is really an extraordinary result.
Yeah, I agree. It really is a head scratcher, and I mean, I put down various ideas, but I don't consider them very. They may. I mean, these are really the only things I can think of. Is that there could be something which has reduced the cross section for the delta SC equals to 0 mode. But yeah, we don't really understand this.
Have you ever come across this before?
No,
Yeah.
not for this kind of sharp mode. You know, either it should be a just a singlet transition, or it should split in 3.
Yeah.
You can, of course, have polarization selection of only one of those transitions. If you use a polarized beam, you could select one and not the others. But in the unpolarized cross section, you should see all of them.
Yeah. Can you think of any way neutrons can couple to a spin-half excitation?
I mean, I've been talking to peers about that. I don't think we really come up with a explanation for it yet. In some ways, I'm thinking that there must be some reason that one of the modes is not seen, but the G factor is already very small. You know, it's just 1.1. So if you wanted to put a central peak in here, that would make the G factor even smaller.
Okay, let me move on next to, if you don't mind, sorry. We've got limited time, I'm afraid. Let me move on next to Priscilla Rosa, because she had her hand raised last time and we didn't get to her. So Priscilla, go ahead and ask your question.
Thank you. Thank you, Collin, for the very nice talk. Perhaps I wanted to start with a comment. So recent electron spin resonance measurements probing precisely gadolinium show that at very, very low concentrations of gadolinium, the resonance is that of an insulator. It's Lorentzian. But as we go, excuse me, as we go up a little bit in gadolinium concentration, then the line changes dramatically and it goes to that of a metal, actually. And to me, that raises the possibility that gadolinium impurities are actually perhaps closing the hybridization gap locally in SmB₆. And I wonder if that could be also an explanation of your results instead of a local screening of gadolinium ions through the Kondo effect. So this would be a local destruction of the Kondo lattice by a non-screened ion, similar to what we know from Kondo hole effects.
This sounds very interesting indeed, and I'd like to think more about those data. At what concentration do you see this transition?
It's very low. It's maybe 0.4%. It's
okay.
Don't take my numbers too seriously here, because I don't remember the exact numbers, but it's some really small concentration.
Yeah, I mean, I think that sounds the way you're thinking about it sounds similar to what we've been considering, namely that the gadolinium as it is introduced creates its own impurity band, which then is able to lead to a screening effect. Yeah. Okay. But I